This is our lab 3 for Poissons Ratio and DIC. In this lab, we're using digital correlation to measure Poissons ratio for various material samples like aluminum, copper, and nylon, and to help us understand how material deforms under load. DIC is widely used. It's non-destructive and a visual measurement application that analyzes and quantify deformation, displacement, and strain by comparing images taken before and after the material is subjected to strain. Poisson's ratio relates to axial strain and lateral strain when subjecting a material to axial loading. In this lab, we wanted to see if we could accurately determine strain and Poisson's ratio for different materials using DIC. The experiment utilized dog bone samples with pattern surfaces pointed facing a digital camera that was adjusted to capture high-quality images. The camera was connected to GOM Snap and GOM Correlate for strain analysis. Control and manipulative vehicles, including a 1 to 3 pound force preload, 20 hertz of frequency, and 120 frame rate, and camera angle and image quality. The video was recorded using GOM Snap and later analyzed with GOM Correlate. The axial and lateral strain was found and analyzed and organized in Microsoft Excel to calculate the Poisson's ratio. We use 5 points at random to find the overall values for each material. This is a sample of our data that we collected for 2 samples of each material: aluminum, nylon, and copper. These are samples of plastic that we use in transversal and axial strain. You can see a lot of variation between the ratio of each sample. Overall, the data for each sample material are different at points and is quite varied, especially but graphically they tend to follow the same trend. The only sample not truly following a trend is our second copper sample.
Most materials should exhibit a positive Poisson's ratio, meaning they tend to contract in perpendicular direction when it is being stretched. In contrast, a negative Poisson's ratio does exist, although it's less common. It shows that the material expands laterally as it is being stretched. Theoretically, we expect the Poisson's ratio for each of the samples to be positive, but in comparison to the theoretical value, the experimental data showed that the Poisson's ratio are all lower than the expected value except for aluminum.
We'll discuss the overall average Poisson's ratio of each material with the virtual value. So, Poisson ratio is important since it helps us as engineers predict how material behave under load. We design around how material expand and contract. But before proceeding, we have to define what literature value is. Literature value refers to a widely accepted characteristic of a material. These values are useful for verifying the experimental result and ensuring accuracy in scientific and engineering applications. From this slide, we can see that the overall average Poisson ratios of aluminum is slightly higher than the literature value of this material, indicating possible experimental inaccuracies. However, the result remains the accepted or reasonable range. For the copper, the average Poisson ratio is slightly lower than the literature value, indicating possible outliers, just a reasonable accuracy with minor inconsistency during experiment. For nylon, the Poisson ratio is slightly. For nylon, the average Poisson ratio is highly unexpected. The average value of 0.39, with error as far as 0.91%. Nylon typically has the same Poisson ratio. It suggests major experimental errors, miscalculations, or unusual material behavior. We have to note that negative Poisson ratio is possible in material known as auxetic material. They behave usually conventional material. So Typical for incorrect Poisson ratio could be measurement in error, leading to an under or overestimation of lateral strain, friction between surface effect, alternate strain measurement, and testing conditions. Implication in real application for aluminum, that is a material that is used in construction. Overestimated Poisson ratio may affect stress strain prediction in structural design. However, on the other hand, it is true in electrical system. Significant deviation can lead to incorrect deformation assumption impacting durability. Nylon that is used in automotive parts, a effective and unrealistic negative Poisson ratio that suggests errors that could lead to design failure in flexible materials.
So in conclusion, our test shows that digital image correlation is an accurate way of measuring Poisson's ratio within a small percentage error. It contains many useful tools like graphing for quick analysis of strain and is also an effective tool for non-destructive material testing. While this experiment provided valuable insights for the DIC, measuring Poisson's ratio, further improvement should be applied to improve the accuracy. The number of samples for each material will also improve the reliability of the average results. Additionally, testing in different environments like heated, cooled, or nonlinear fields will also allow us to explore the material's capabilities. For future works, it should also consider extended applications like using DIC to determine the shear modulus of materials.
This concludes our presentation on Poissons ratio and DIC testing. And the references we use are the engineering toolbox and scholastic.com for our Poissons ratio actual values. Please contact us further with any questions.